Thank you. Thank you very much for coming today. I hope there is more than 0 people in this virtual audience. At this time, I'm Alex Gilgur. I work at Facebook, and I'm also a PhD candidate at Stevens Institute of Technology under Dr. Jose Ramirez-Marquez. We are going to talk about people's mobility more in terms of permanent mobility. We are trying to answer the question, why do people pick up and leave and go to a new place? It can be opportunities of new employment, it can be better infrastructure or more suitable infrastructure, it can be more affordable or more prestigious, stable. People think they will be happier in the new place, and so on. But if we look at all the factors that we can collect about these parameters, it becomes a fairly big smorgasbord. And this presentation is about an attempt to put this into a framework that helps to better interpret all these parameters. So we start with data collection, we do some exploratory data analysis, we fill in the empty data cells, we normalize or standardize the data, and then we find out that there is a lot of multicollinearity. For example, many organizations collect the same variables and they call them differently. Just one of the examples. So we need to do principal component analysis, which we will talk about later. Basically, it is rotating the data, or rather the coordinate systems in such a way that we end up with orthogonal principal components. From there, we can try some modeling, because ultimately we are not as much interested in how much variance this or that principal component explains, which is what PCA answers. But we are interested in how these components affect the fit of the model of predicting migration. And once we have done that and we've identified the importance of principal components for modeling, then we can do some reverse matrix algebra and identify the mobility factors. That's the whole presentation in a nutshell. Data come from, like I said, many sources. I focused this presentation on government sources, US government. It's Community Commons, Bureau of Labor Statistics, of course, Census Bureau, CDC, US Department of Agriculture has a very interesting number of data sets, and so on. And if we look at the correlations, we already see that, for example, net migration is one thing, but domestic and international migration are very different things. You can see here that as much as international migration is affected, or is correlated rather, with education level, right? We have 21, 22, 23, and 31 variables numbers. They are all in the purple for international migration, and they are all equally in the orange, which means they're negatively correlated with domestic migration. Similar thing with some of the census data, and so on and so on. So we have some interesting effects. We have some possible correlations, because of course, the number of unemployed people, unemployment rate, which is number of unemployed per 1,000 or per 100,000 people, and population, they will be all collinear, they will all be correlated. We may even need to go into logarithmic relationships, but as a first step, let's just look at linear relationships and go to principal component analysis. Oh, and in addition, Census Bureau models the data between the census collection times. Census collection is being done once per decade. During the decade, the population movement is modeled based on the birth-death process. I'm using birth-death as a mathematical term, not as a sociological term, but they have some complicated and sophisticated, rather, models to predict how between 2010 and 2020 the population is going to develop, how migration is going to affect population, and vice versa, because smaller counties, for example, usually see less migration going into them. Whether it's causal or not, that's a second question, but that's one of the important questions. So first, eliminate multicollinearity. The best way to do it is by principal component analysis, because it's mathematically very simple, and mathematically it creates orthogonal variables, which are called principal components. In addition, it tells us how much of the variance each of the new principal components explains. So here we start with 25 principal components. We see that there are some that are very high, like the first one is higher than 45% of the variance is explained by it. And there are also some principal components that are very low in the power to explain the variance in this blob of data, multidimensional blob of data. So we can cut it down by doing another principal component analysis and another PCA and so on and so forth. The problem with this is thresholds are arbitrary. The other problem is they don't tell us anything about how this affects our model. If we go from 25 PCs to 13 or even to 5, how much penalty are we taking in the quality of our model? If we explain with 25, we'll have probably a better model. We do run the chance of overfitting. But if we go to 5 principal components, we are most likely not going to overfit, but we may run into a problem of underfitting. So we need to model it. But how do we model? We don't know the structure of the model. We don't want to be tied into linear modeling, right? Because we don't know that our model is linear. We want to go non-parametric. And the most accessible method for it is random forest regression. It is one of the most robust methods for modeling multidimensional data. It is non-parametric, therefore we can use it even if we don't know what the underlying model is. And it also gives us, as one of its outputs, feature importance based on the amount of information that this feature, this principal component carries, okay? So let's daisy chain it all. We started out with correlation analysis. Then we did PCA. We identified the principal components, or we built the principal components rather. And now we go into random forest regression. So we have, like with any regression, we have the predicted value of the output variable, and we have the observed value of the output variable. So we can plot one against the other. We can measure the correlation. We can take the R-square of it. And just like we always do in machine learning, we break the data down into the training and the testing data sets. And now we have the R-square. Now the question is, so what? We can then do the inverse. So we have cut down the principal components, we have fitted R-square, and then we can go back. What is our R square? In this case, it's 0.78. Let's run it again, but remove some more principal components or add some more. Has it changed? Has it changed by much? By how much? What's more, we can cut off PCs at the modeling level. What if we remove the bottom 5? Like in this case, we have 1, 2, 3, 4, 5 features as unimportant. We don't know what they are, but we think they are too small to matter. Let's throw them away. Now, what is the R square if we don't use them? Do we need to add them back? So now we are in a different ballgame. Now we can identify the exact combination of the factors, and now we know we can come up with the right features for modeling. How we model, that's a separate story. But first we need to go back to the original features. So we have identified correlated variables, we have applied PCL, and we used PCA, and we have used random forest regression, and we identified the final important principal components. Now we do the next step, transform it back to the original features. And that is what we are doing in this presentation, and this is what we are working on. Further, now that we have identified the features, now we can look at the right model. We can look at the physical model of migration. We can use equations similar to the ones used in, for example, absorption, and in desorption. We can use models used to describe fluid flow even, because large masses of people behave similarly to fluids, or gases rather. They feel the volume, they move from high pressure to low pressure, and so on, from low volume to high volume, in terms of possibilities to open, possibilities to expand. Not necessarily people move from cities to rural areas. It doesn't always happen. People still want to live, many people still want to live in cities, but we move to suburbs, for example. They want to move out of the confined city life to suburbs. Now we can model it by using equations based on the analysis that we have performed. So from here, we can infer the pressure and the resistance terms, the delta P and the R, in terms of sociological, economical, psychological terms, and financial. And from there, we can build a model predicting movements of large masses of population. So it's a high complexity multivariate problem that we are solving. There is a lot of interaction, overlap, multicollinearity. We want to understand the underlying processes, and by understanding, it means we can model them, we can derive them mathematically, and we have described how this can be achieved based on publicly available data and using the standard machine learning techniques. Thank you.